Welcome back to the second part in our bonding series. Just want a quick review over the types of bonds we learned in the last video. We talked about covalent bonds, which break down into two categories, nonpolar covalent and polar covalent. Remember, in nonpolar covalent bonds, the electrons are shared equally. So as you can see here around the two hydrogen nuclei, the electron cloud is evenly dispersed. In a polar covalent bond, the electrons are shared unequally, but the point is that they are still shared, which is what makes them covalent. So here you'll see that the electron cloud is dispersed unequally. The oxygen gets the electrons for most of the time because oxygen is more electronegative than hydrogen is. Remember those periodic trends. So we have our partially negative sign for oxygen and our partially positive sign for hydrogen. And then we have ionic bonds. And remember, in ionic bonds, the electrons are not shared at all. In fact, one electron is completely stolen from another atom and given to a new one. So here, this chlorine atom has stolen an electron from the sodium, and so it has become completely negatively charged. The sodium atom has become completely positively charged, turning them both into ions. And then that positive and negative charge causes a force of attraction there, and that is the ionic bond. Okay, so what are some of the effects of these different bond types, or we could talk about what are their characteristics? So I'm just going to talk about three main classes here: melting point and also freezing point. Those two are actually the same thing. Solubility and conductivity. Okay, so if we're talking about an ionic bond, they usually melt at higher temperatures, and that's because you can think of those cations and anions that they form, the positive and negative charges, like little magnets. And those magnets are really strong, and so you have to break all of the ionic bonds before you can melt any of the sample. And so it takes longer to do that, which means the temperature gets higher and higher. It requires more energy to break those bonds. Okay, if we're talking about their solubility, solubility means being able to dissolve in water. The reason that they're able to dissolve in water is because water is a polar molecule. And remember, polar has a positive and negative side to it. Right here, the hydrogen part is positive and the oxygen part is negative. You could think of our water molecule like this. If we have the hydrogen bonded to oxygen here. Okay, that's a water molecule. So between this hydrogen and oxygen here, we're looking at one side of a water molecule. So most of the electrons are going to spend their time around the oxygen and less time around the hydrogen. So if I was drawing this, I might draw it like that, but I would do it for both of these bonds here. Okay, so the oxygen's got a whole bunch of electrons or density around it, and the hydrogens don't have very much at all. So again, we say that these are partially positive and that the oxygen is partially negative. So when you put a polar molecule in there with an ionic molecule, the positives and the negatives kind of pair up, and they're allowed to be separated because of that. Alright, then we have conductivity. And generally speaking, ionic compounds will conduct electricity, and that's what conductivity is talking about. Can it conduct electricity? And it can, because the charges in electricity, the electrons, have somewhere to move because there are charges in an ionic bond. Okay, now let's talk about covalent bonds. The melting point of covalent bonds are much lower than ionic, and that's because they share the electrons. So the actual molecules that are floating around all together, they are actually attracted to each other also, but they're weakly attracted to each other. Now, the electrons that bond covalent molecules together are strong, but the forces that hold entire molecules together are weak. And so, because of that, they have a lower melting point than ionic bonds do. We're going to talk about what these weak forces are called in a later video. Alright, let's talk about solubility of covalent molecules. Generally, they are not able to dissolve in water. Okay? There are situations which they can. One of the best ones is sugar. Sugar is a covalent molecule, but it does dissolve in water. Again, the reason why they don't dissolve in water has to do a lot with these forces that we talked about up here. And even though they're weaker forces, they are still strong enough to prevent the water from being able to come in and pull the molecules apart. Generally, covalent molecules do not conduct electricity. That's because there's no charge, especially if it's a non-polar covalent bond. There's absolutely no charge in there, so they won't conduct electricity. A polar covalent bond might conduct electricity a little bit, but not 100% like an ionic bond would. Okay, the fourth and last type of bond is the metallic bond. Okay, obviously, metallic bonds happen between metals. Metals or metallic bonds have what's called a mobile cloud of valence electrons. That mobile cloud of electrons just means that every single electron can move around every single metal atom. So they're not fixed like the electrons are of any of the other types of bonds. The electrons are forced to stay around their own atom's nucleus, but in a metal, the electrons can actually move between the nuclei. So you could have, an electron that belongs to this atom over here could actually zip around and travel all around any of the other metal atoms that are there. Their ability to do that is what allows them to have high electrical and thermal conductivity, meaning they conduct electricity really well and they conduct heat really well. Metals also form their own semi-crystal lattice, I guess you could say. It's not really a crystal, so to speak, like the crystals we saw for salt, but they do form this geometric arrangement. It's not always a square like this, but they do form a rigid geometric pattern in their molecular structure. Here's another example of that mobile cloud of electrons where the electrons are free to move around anywhere they want to in the sample of metal. Okay, here are two characteristics of metals that you need to know. The first one, malleability, is the ability of a substance to be hammered or beaten into thin sheets. So a good example of a substance that could do that would be aluminum, because we have aluminum foil, which is a very thin sheet. So something had to beat that down, roll it, and make it very, very thin. And then we have ductility. Ductility is the ability of a substance to be drawn or pulled into a small opening to produce a wire. Obviously, we know copper would be a good example of that because we have tons of copper wire. Okay, so now we want to be able to classify what kind of bond we're going to have based on the electronegativities. We did this at the very beginning of the last video, so now here's some practice for us. Okay, we have an example down here just like we did in the first video. We want to see what a bond between sulfur and hydrogen would be classified as. So we had this bond here between sulfur and hydrogen, and I want to know what kind of bond is that. You have four choices. It can be nonpolar covalent, polar covalent, ionic, or metallic. So what kind is it? Remember, you have this type of bond range up here for their electronegativities, and all we have to do is subtract. So remember, on the back hand side of your periodic table, you have the electronegativities of every element, and you're just going to subtract to figure out what the difference in their electronegativity is. Then use your chart up here to classify the type of bond. So if we were using sulfur and hydrogen, here's sulfur's electronegativity, here's hydrogen, and we get a difference of 0.48. So if we look up here in our range, we see that 0.48 falls right here. It's between 0.41 and 1.67. Therefore, it's a polar covalent bond. Which atom's the most electronegative? That one's sulfur, because it's got the higher electronegativity here. Okay, so I want you to go through and do the rest. Alright, fill out the rest of this chart, and we'll come back in just a second and see what you got. Alright, here's what we've come up with. Ionic, polar, ionic, nonpolar for the bond type, and then sulfur, chlorine, chlorine, and oxygen for the most electronegative atoms. And then, of course, here's all that math. Now, in your notes, that's where this chart comes from. This is only the first 5, okay? And then you're responsible for doing the next set. And I hope that you actually took the time and tried to do those before they popped up on screen. Either way, if you need more help, come see me for tutorials, but hopefully this is simple enough for you. Okay, a couple of more vocabulary words. Let's talk about what is a molecule. A molecule is a group of atoms that are held together by a covalent bond. A diatomic molecule, let's break that down. Okay, di means 2, and atomic is obviously referring to atoms. Okay, let's kind of give me some room here. 2, and then atomic is talking about atoms. So a diatomic molecule is a molecule that only has 2 atoms in it. Okay. We have several diatomic molecules on the periodic table that you need to memorize. The easy way to memorize them is anything that ends in gen will form a diatomic molecule. So we have hydrogen, nitrogen, oxygen, and any of the halogens. Okay? And when we say they form a diatomic molecule, it means that 2 of those elements group together. So we have hydrogen, nitrogen, oxygen, and then here are all of our halogens. Quick review for you. Remember, this column right here in the periodic table are the halogens. They're right next to the noble gases. So this column is our halogens. So that's why all of these are also diatomic molecules. Okay, atoms in general will try and attain a noble gas-like configuration. So when we're talking about configurations, remember we need to go back to our electron configurations. The 1s2, 2s2 stuff, okay? And when we say that they're trying to attain that, it means that they're trying to look like a noble gas. So here we have all of our noble gases. Helium is a little bit different from the rest of these guys. Notice that helium has 2 electrons in its valence energy level, but every single other noble gas has 8 electrons in its valence energy level. Okay? So when an atom bonds with something else, it tries to do it in such a way that it ends up with 8 electrons in its valence electron energy level. And that is so that it can look like one of these noble gases. This is also why noble gases don't really bond with anything else, is because they already have 8 electrons in their valence energy level and they're happy, so to speak. So hydrogen tries to look like helium because helium is the noble gas at the end of hydrogen's row. So helium, as we just saw up above, looks like this, where it's got its 2 electrons. So when 2 hydrogen atoms come together, and they bond with each other, what really happens is they share those 2 electrons, and so now each of these hydrogens gets to feel like it has 2 electrons zipping around it. Okay, so this electron can zip back and forth between both hydrogens, and so can this one. So in that covalent bond that they have, their nonpolar covalent bond, they're both getting to feel like they both have 2 electrons, so that they look like helium. All right. Other atoms try and gain 8 electrons because the noble gas at the end of their row have 8 electrons. This is called the octet rule. Okay, oct is the prefix, I guess you could say, that means 8. All right, so like how many arms does an octopus have? 8. All right, so the octet rule says that atoms will lose or gain electrons in order to acquire an 8 electron configuration in their valence energy level. Okay, metals lose, nonmetals gain. We've already talked about that. There are a few exceptions to the octet rule. Okay, hydrogen breaks the octet rule because it only wants 2 electrons and not 8. Boron breaks the octet rule because it only has 3 electrons in its valence energy level. That's an odd number. Usually it goes in even numbers. So boron tries to obtain 6 electrons so that it can become even rather than odd. And then there's some elements here that you will see pop up regularly that break the octet rule. Helium because it's 2, beryllium, phosphorus, sulfur, and xenon. Those will break the octet rule, and traditionally when you see them, they're only there because they are breaking the octet rule and somebody's trying to trick you. Okay. Another thing to understand is that any element in the 3rd row or greater can break the octet rule because they have d orbitals. Remember, the 3rd row of the periodic table, the 3rd energy level, is the first time that a d orbital appears, and because those elements have d orbitals, they can place electrons in those d orbitals rather than filling them normally in some occasions when they're bonding, and that allows them to break the octet rule. So these elements up here are just the ones that you'll see most often, but please understand that any element in the 3rd row or beyond can break the octet rule. Okay? Alright, so we're going to talk about electron dot notation. This is a form of electron configuration, but we're only going to show the valence electrons, and we're going to kind of do it pictorially, where we're going to use the element symbol and we're going to place dots around it like you've been seeing me do. So here's what something like that would look like. Let's say that I were doing an electron dot notation for hydrogen. You write the atomic symbol H for hydrogen, and you put 1 electron there because there is 1 electron in the valence energy level for hydrogen. Okay, carbon. You write the atomic symbol, and then you need to put the valence electrons around carbon in their dot form. Okay, well, how do we know how many valence electrons an element has? Here's a simple way to know that. I want you to put this on top of your periodic table if you haven't already, okay? There's 1, 2, 3, 4, 5, 6, 7, and 8. That is how many valence electrons the elements have in that group. So all of these have 1 valence electron. These have 2. We're not going to talk about these yet. And there's 3, 4, 5, 6, 7, 8. Okay, so it's very simple to know how many valence electrons an element has. Okay, so if we were doing chlorine, it's in that 7th group, so it's got 7 valence electrons. There are different types of electrons. When they're paired up like this, they're called pair electrons. When they are alone by themselves, they're called unpaired electrons or lone pair electrons. Okay, so here we have unpaired electrons or lone pair electrons. Alright, so let's try and do the electron dot notation for these elements here. Alright, we've got lithium. How many valence electrons does lithium have? 1. So we would put 1 valence electron there. Okay, how many does fluorine have? 7. Alright, now when we start placing these electrons around the elements, there's a certain way to do it, okay? So I'm just going to pull fluorine out real quick. When you do it, you're going to use the top, the bottom, and the left and right hand sides, okay? Sometimes people place them in the four corners. Alright, that's fine too. Either method is fine, I don't care, it doesn't matter. But when you place the electrons, you need to do them one at a time on each of those sides before you come back around and pair it up. That's following Hund's rule. Remember Hund's rule from our electron configuration section, where everybody gets one electron first before anybody else gets a partner? You have to follow that, or you'll end up with a funky looking dot diagram and it'll be wrong, okay? So make sure that you go around and give partners only after you have done each side with an electron, okay? So here's fluorine's configuration where it's got its 7 electrons, okay? Alright, how about magnesium? How many valence electrons does it have? 2. Very good. So we can do 1 here and 1 here. Alright, and how about aluminum? How many electrons, valence electrons, does aluminum have? 3. Very good. So we'll put our 3 valence electrons here. Okay? This practice is in your notes, and there's a lot more of them to do, so I want you to go through and do the rest of those in your notes packet. And I think we'll leave it here for this video. Thank you so much for learning with me today, and I will see you next time.